Hi everyone, this is Madhav. I'm back here again talking about linear algebra, but with a little bit less math than usual, a little bit more visuals than usual. Last video, which I will refer you to, I explained very basics of linear algebra. This video, I am going to talk about the concepts that we referred to last time, so if you haven't watched that and you don't understand this, that's kind of why. But if you do understand vectors and matrices, then you're in a good position to watch this video. And you don't need to be familiar with all of the intricacies, but you do need to know about matrix multiplication and matrix vector multiplication. With that out of the way, let's get started. We're going to be talking about how we can use some visual properties to speed up very common computations that we do. So this is going to be a topic that we often use in practical applications, and here I'm going to try and show you the intuition, the visuals behind it. So let's start off with our standard basis vectors. You see them very tiny down here. They're all pointing in different directions, and we have this matrix A that we have defined. So in online courses, you often are told about what to do if you want to say multiply matrix vector multiply A with any of these vectors. So you see I have my software here computing the results of A matrix multiplied by x1, y1, z1. You're often told how to compute this, but I want to show you the intuition behind what is actually going on. So you'll notice that I am starting with my standard basis vectors, they're special vectors. And when I multiply my matrix with the standard basis vectors, you see that I actually get out the columns, each of these columns, as answers. You see? I get the first column being -2, -2, 4, and that's what I get when I matrix vector multiply A by x1. Same thing with y1 and the matrix vector product of A and y1. Same thing with z. So when I'm taking my standard basis vectors, the special thing about them is that they matrix vector multiply with any matrix to just get these columns that you see here. So the product is just the columns. It's a useful property. But the visual interpretation of this is that our matrix A here, it is taking these standard basis vectors, all three of them, and it is transforming them into these new vectors. Let me show you this one at a time. So let's start with our x1 vector, which you can see here in pink. When I take matrix A multiplied by x1, then x1 goes from being, here to now pointing in this new direction. It's been transformed. Let's turn to y1. Let's see. Before we had y1, it was this orange vector pointing in this direction. After I multiplied by A, again, it's been transformed. It's now pointing in a different direction. And then, last of all, I'll show you Z1, but let me declutter our space here. So Z1, it started off pointing upwards like this. After it got multiplied by A, now it's pointing in a different direction. So this is a very fundamental idea. When we have matrix vector multiplication, anytime we have it, the visual interpretation is we're taking some matrices, some vectors like this, and then transforming them into some new vectors like this. So this is a very important concept that often gets neglected in textbooks. They don't talk about how matrix vector multiplication anytime is just always transforming some vectors from where they used to be to someplace new. Now, of course, this doesn't just, stop once, right? We went from our original vectors that are so small that you can hardly even see them now. We went from those to some new vectors, and we can keep doing that. So you see down here, I've done it again. I took the vectors that I have here, and then I multiplied them again by the matrix A. And so we will get again some transformed vectors. So from x2, the one in purple, before it was like this, now we're going to transform it and it's going to start pointing in a new direction again. Same thing with y2. Before it was this orange vector in this direction, now it's going to start pointing in a new direction after it's been multiplied by matrix A. And then finally with Z2, so this vector here, it's also going to be transformed in a different direction after being multiplied by matrix A. So the key thing that I want you to get out of this visual is just understand that any matrix vector product, no matter how many times we're multiplying a matrix by a vector, it's always going to take a vector pointing one way and then turn it into a vector pointing another way. So here, this, let's say we focus on this vector right here, Z3. The way that I got this was to multiply A by Z2, but A by Z2 was just A by Z1. To write that out, Z2 itself, I could replace that with this equation up here, A times Z1. So if I replace that, you can see nothing changes. But now I just have a matrix multiplication, and then I have a matrix vector multiplication. To make that more intuitive, let's say I have B is equal to A times A, or A squared. This gives me a new matrix that I can use to multiply up here. So I can let Z3 to be equal to B times Z1 instead of A times Z1, just because, B is equal to A times A. And this doesn't change anything because A times A, matrix multiplication, just gives me a new vector. It just gives me a new matrix. And so fundamentally, every matrix multiplication, it's kind of just like, okay, I have two matrices with potentially different transformations that they represent. now I create a new transformation out of that. And so this is the fundamental graphical intuition about matrices and vectors. Matrices are transformations for vectors. They just take some vectors pointing in one direction, transform them into another direction. And this is the fundamental operation of matrix vector multiplication. When it comes to matrix multiplication, multiplying two matrices together, all that means is we're just creating a new transformation. Before, A represented one transformation. Now, B, it represents another transformation. There's nothing special about it. It's just another transformation. And so we can use B just like we used A. We can multiply a B by other vectors, and now we have matrix vector multiplication, which is a transformation. I know I'm saying a lot of words repetitively, matrix, vector, transformation. It can be easy to get lost in that. So if nothing else, just remember, we started off with some vectors pointing one way and then they ended up pointing another way. And then you'll be like, that's interesting. Okay, so that's what's going on whenever you're computing some matrix vector multiplication. So now that we've talked about matrix multiplication and matrix vector multiplication as graphical concepts, visual concepts, I want to talk a little bit about basis vectors, which is a topic that I explained a little bit in my last video. So basis vectors, quick recap, they just mean like you take some vectors, and the special thing about these vectors is they add up to another vector. So you can see here I have two vectors that add up to x2, right? So we say that these two vectors, this black and gray vector, they are basis vectors for this other vector, because they're kind of like the building blocks, the basic Lego blocks that we stack together to make this larger vector. Now, one thing that you should note is that matrix, the structure of a matrix, I noted earlier how all of the columns are just equal to the transformations of these standard basis vectors. So 1, 0, 0 turns into -2, -2, 4, and so it's in the first column. 0, 1, 0 turns into -4, 1, 2, second column, and so on. So whenever you read what is called the standard matrix, but whatever, just the matrix, whenever you read a matrix, what it really means is this matrix is taking the standard basis vectors and it is turning them into these other vectors via transformation. So you can get that information directly from reading the matrix. The other thing that's interesting is that here, so I have x2, it is a times, the standard basis vector here. So I have x2 here, and I've expressed it in terms of two not standard basis vectors, but two basis vectors, these two right here. What happens when I matrix vector multiply a into x2? Well, I showed you earlier, I get x3. Alright, that seems feasible enough. Can I relate x3 to x2 in terms of these two basis vectors? What does that mean? Well, before I used, these two black vectors as building blocks for x2. Then I transformed x2 using my matrix. Okay, can I still use my building blocks to represent this transformed version of x2? Can I add some variant of these together to still get this new vector? Well, okay, I went from x2 to this new one by matrix vector multiplying it by A. What if I did the same thing with my building blocks? So I matrix vector multiply each of my building blocks by A. You see, I took one building block, multiplied it by A to get this, took the other building block, multiplied it by A to get this, and then now my transformed building blocks, they still add up to my transformed vector. This is a key idea because it means that sometimes we can take, let's say, a computation like A times x2, and we can break it down into other computations that might be easier. So mathematically speaking, we know that these two vectors, P and Q, you can see them here, P and Q, these two vectors, they add up to make x2. So P plus Q equal P2 plus Q2 equals x2. Okay, if we transform x2 using the matrix A, then we can still get P2 plus Q2 equals the transformed version, except we have to transform both PQ and Q2 as well. So hopefully this is kind of making sense. It's kind of like you're taking, x2, giving it a new coat of paint, you're transforming it a little bit. And if you do the same thing to your building blocks, your fundamental Lego blocks, then you can use them again to, build up the new version of x2. Now, the last thing that I'll talk about is we could have taken any basis vectors here, right? We could have taken any two vectors and then, or even more than two vectors, and then added them up to get these pink vectors. How do we choose some vectors that are going to be nice to work with? Some vectors that are going to speed up our computations? The answer turns out to be that we want to use some things called eigenvectors. I'll first talk about eigenvectors in general, and then in a separate video we'll talk about how do we apply all this? How do we use the eigenvectors in a computation? So, eigen is a German word that means same, alike. So, or own, I suppose is a more literal translation. Own, so my own thing. This kind of makes sense if you see what eigenvectors are. So let's say I have this vector right here. Should I zoom in? I zoomed in a bit. You see I have this vector right here. If I matrix vector multiply it by A, this special eigenvector, I get a multiple that is just pointing in the same direction as A. It's just bigger. So it is like this initial vector, except it's just a multiple of it. And if we look at the numbers here, we went from negative 231 to negative 693. You can see that this is a third of this. So what I'm saying is this new black vector, it is 3 times this original vector. If I try and multiply it twice, okay, still pointing in the same direction but bigger. Alright, how about 3 times? Still pointing in the same direction but bigger. So this is the special thing about eigenvectors, alike vectors, own vectors. They're just pointing in their own direction all the time, no matter how many times you matrix vector multiply them with a particular matrix. That's why they're called eigenvectors, alike, own, same vectors. Most vectors, they don't follow this property, right? Like you saw when I had P2, for example, it's so small we can barely see it, so let me zoom in here. When I had P2, and that's the black vector, and I multiplied it by A, it pointed in some different direction. That's what usually happens. Eigenvectors, they're special. We can multiply them by A and they stay pointing in the same direction. Now, different matrices will have different eigenvectors. So this, particular vector, -2, 3, 1, that's not special, right? There's going to be some matrices that you can multiply this by, and it will point in some different direction. It's only special in the context of this particular matrix A. So every matrix will have its own eigenvectors. Well, not every matrix, but many matrices will have their own eigenvectors. Some matrices don't have any. But for matrices that do have eigenvectors, that's kind of neat, right? What happens if we can use these in computations? Well, the computation's quite easy. We know what to expect, right? Like, no matter how many times I multiply by A here, you just know that it's going to be 3 times some multiple of the original vector I had. So this is the thing that makes computations with eigenvectors very easy. We can easily predict what the result will be. And this is why eigenvectors, they're going to be very nice building blocks for other vectors. They're going to be very nice basis vectors, because no matter how many times we try and transform these building blocks, they're still going to be predictable. We're still going to be able to very quickly guess what the result will be using the properties of eigenvectors. So in the next video, we're going to talk about this procedure in full mathematical detail and glory. It's going to be very messy, I think. However, you just need to understand the visual building blocks for the concepts. You just need to remember, I had a vector pointing this way, it went into that way. I multiplied 2 matrices and it just gave a new matrix, which was just a new transformation. Basis vectors, they're just the building blocks. We can add them up to get a particular vector, and we can even transform the basis vectors and get a transformed version of the vector. And eigenvectors, they're just doing their own thing. They're pointing in their own direction all the time, no matter how many times we multiply them with a given matrix. If you understand these concepts, you're going to be able to picture something in your head when we go through the computations in the next video.